For most of human history, space was never questioned. It was simply there, an invisible stage on which everything happened. Planets moved through it, light crossed it. You and I exist inside it. When you stretch out your arm, when you walk across a room, when you look up at the night sky, you instinctively assume space is continuous, smooth, unbroken, like an endless sheet. But physics has taught us something unsettling. Many things we once believed to be continuous are not. Matter is made of atoms. Energy comes in packets. Light arrives in quanta. So the question quietly emerges, is space itself continuous, or is it made of tiny pieces? At first, this sounds almost childish, like asking whether reality is made of Lego blocks. But this question sits at the center of modern theoretical physics. Because if space is not smooth, if it is pixelated at some unimaginable scale, then everything we believe about distance, motion, and even time must change. How humans first imagined space. In ancient Greek philosophy, space was thought of as an empty container. Aristotle believed space could not exist without objects. Later thinkers imagined space as a passive background, something that does nothing but allows things to exist. This idea survived for centuries. Even Isaac Newton believed space was absolute, a rigid, invisible framework that exists whether anything is inside it or not. Newton wrote, "Absolute space in its own nature, without relation to anything external, remains always similar and immovable." In this picture, space is perfectly smooth, infinitely divisible. You can always split a distance in half, and then in half again, forever. No pixels, no grain. Einstein changes everything, but not this. In the early 20th century, Einstein shattered Newton's view. Space was no longer passive. It could bend, stretch, and curve. Mass tells space how to curve. Curved space tells matter how to move. This was the birth of general relativity. And yet, even here, space was still smooth. Einstein's equations assume spacetime is a perfectly smooth geometric fabric, like a perfectly smooth rubber sheet. So even the most revolutionary theory of space ever created still quietly assumed space has no smallest unit. But then, physics went somewhere Einstein never wanted it to go. The quantum problem quietly appears. At very small scales, nature behaves differently. Electrons do not orbit smoothly. Energy jumps. Fields fluctuate. Quantum mechanics describes a universe that is grainy, probabilistic, and discrete. And now physics faces a deep tension. General relativity, smooth, continuous spacetime. Quantum mechanics, discrete, quantized reality. Both are astonishingly accurate. Both are experimentally confirmed. But they cannot both be fundamentally correct at the same time. And this is where the question returns, more seriously than ever. Is space itself quantized? If space is smooth, we can divide distances forever. If space is pixelated, there is a smallest possible length, a limit beyond which the idea of distance no longer makes sense. And physics has a name for that suspected limit. In the late 19th century, physics encountered a problem it could not solve. Black-body radiation did not behave as classical physics predicted. The solution came from an unexpected idea. Energy might come in discrete packets. This radical proposal was made by Max Planck in 1900. To make the equations work, Planck introduced a new constant, now called Planck's constant, denoted by h. He did not realize it at the time, but he had opened a door that leads directly to the structure of space itself. Constructing the smallest possible length. Using three fundamental constants, the speed of light, c, Newton's gravitational constant, g, and Planck's constant, h bar, physicists can construct a natural length scale. This length is called the Planck length. Its value is approximately 1.6 times 10 to the minus 35 meters. This is unimaginably small. To give perspective, an atom is about 10 to the minus 10 meters. A proton is about 10 to the minus 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. At this scale, our current theories stop making sense. Why the Planck length matters. The Planck length is not just very small. It represents a theoretical boundary. Below this scale, quantum fluctuations of spacetime become violent. Gravity and quantum mechanics collide. The concept of distance loses meaning. Physicist John Wheeler described this regime as quantum foam, a turbulent, bubbling structure of spacetime itself. Here, space is not smooth. It is restless, unstable, possibly discrete. Physicists do not know for certain that space is pixelated at the Planck scale. This is crucial. The Planck length is not proven to be the pixel size of space. Rather, it is the scale at which our current theories fail. But failure itself is informative. It suggests we are missing something fundamental. And many physicists believe that something is the discrete structure of spacetime. A subtle but profound shift. If space has a smallest unit, motion becomes a sequence, not a flow. Distance becomes counted, not measured. Geometry becomes combinatorial, not continuous. This is no longer classical geometry. This is a quantum geometry. And multiple research programs are trying to describe it. Physicists have proposed several serious, mathematically rigorous frameworks in which space is not smooth. These are not science fiction. They are active areas of research. Let us explore the most important ones. 1. Loop quantum gravity, space made of loops. Loop quantum gravity, LQG, is one of the leading approaches. It attempts to quantize spacetime itself. Not particles within space, but space itself. In this theory, space is made of tiny, discrete chunks. These chunks are described by mathematical objects called spin networks. Areas and volumes have minimum possible values. In LQG, space resembles a woven fabric. Not continuous, not smooth, but granular, like a cosmic mesh. Physicists Carlo Rovelli and Lee Smolin have been central figures in developing this theory. According to LQG, you cannot divide space indefinitely. There is a smallest unit of area and volume. Does this mean space is literally pixelated? Not in the way a computer screen is. This is important for intuition. The pixels of space are not arranged on a fixed grid. They are relational, dynamic. Space is not a thing inside something else. Space is the network itself. As of today, no direct experiment has confirmed space quantization. The Planck scale is far beyond current technology. However, physicists look for indirect signals, tiny violations of Lorentz symmetry, energy-dependent speed of light, quantum gravity effects in cosmology. So far, all results are consistent with smooth spacetime within experimental limits. But within limits is the key phrase. So where does this leave us? Space appears smooth at every scale we can probe, but theory suggests that smoothness may be an illusion, like calm water hiding molecular motion beneath. In physics, there is a quiet but powerful idea. A theory can be correct without being fundamental. Water feels smooth to your hand, but at a deeper level, it is not. It is made of molecules. The smoothness emerges only because your fingers are far larger than the molecular scale. Physicists ask the same question about space. Is space-time fundamentally smooth? Or does it only appear smooth because we are too large to see its structure? Effective theories. Why this matters. General relativity may be an effective theory. That means it works extraordinarily well at large scales, but it may break down at very small ones. This is not a failure, it is normal in physics. Classical thermodynamics works beautifully even though it ignores atoms. In the same way, space-time geometry may emerge from something deeper. What breaks first when space isn't smooth? At extremely small scales, distances fluctuate, geometry becomes uncertain. Here and there lose sharp meaning. Physicists believe that locality itself may fail. Events may no longer have a precise position. This is a profound shift. It suggests that space is not the stage, but the result of deeper relationships. Reference: Conceptual Foundation. Steven Weinberg, Dreams of a Final Theory. John Wheeler, Geons and Quantum Foam, 1950s through 1960s. If smooth space is not fundamental, what's underneath it? One of the most radical ideas in modern physics is this: space may emerge from information, not metaphorically, literally. This idea comes from black hole physics. The black hole clue. In the 1970s, physicist Jacob Bekenstein discovered something shocking. The entropy of a black hole, a measure of information, is proportional not to its volume, but to the area of its surface. Later, Stephen Hawking confirmed this through quantum calculations. This led to a strange conclusion. The information content of a region of space may live on its boundary.
This is not how smooth space behaves. The holographic principle. This insight evolved into the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind. It suggests a three-dimensional volume of space can be fully described by information on a two-dimensional surface, like a hologram. In this picture, space is not fundamental. Geometry is encoded. Distance emerges from information relationships. ADS-CFT, a concrete example. In the late 1990s, physicist Juan Maldacena discovered a precise mathematical realization of holography, known as ADS-CFT correspondence. It shows that a theory with gravity in higher dimensional space is equivalent to a gravity-free quantum theory on its boundary. This is not philosophy, it is mathematics. In these models, smooth spacetime emerges from quantum entanglement. Geometry is built from correlations. Reference: essential. Leonard Susskind, The Black Hole War. Maldacena, 1997, The Large N Limit of Superconformal Field Theories. Brian Greene, The Fabric of the Cosmos. If space emerges, then pixelation may not mean blocks. It may mean relationships. Different theories propose different answers, but they agree on one thing: smooth space cannot be fundamental forever. Loop quantum gravity, revisited, deeper. In loop quantum gravity, space is made of spin networks. Nodes represent quanta of volume. Links represent quanta of area. Area and volume have discrete spectra. This is not assumed, it is derived mathematically. Key idea: geometry itself is quantized. String theory's different approach. String theory does not explicitly pixelate space. Instead, fundamental objects are tiny vibrating strings. Different vibrations produce particles. However, when string theory is pushed to its limits, minimal length scales appear. Attempts to probe smaller distances fail. This suggests that even if space isn't made of pixels, it resists infinite resolution. A quiet agreement. Despite their differences, loop quantum gravity, string theory, causal sets theory all suggest that there is a limit to how finely space can be resolved. Reference: Carlo Rovelli, Quantum Gravity. Brian Greene, The Elegant Universe. Raphael Sorkin, Causal Sets Papers. This question matters deeply. Physics is not complete without experiment. The difficulty: the Planck length is far smaller than anything we can probe. Even the Large Hadron Collider is 16 orders of magnitude too weak, so physicists look for indirect effects. Possible signals. Researchers search for tiny deviations in the speed of light, quantum noise in spacetime, imprints in the cosmic microwave background. Some proposals involve gamma-ray bursts, gravitational waves, and early universe inflation. So far, no confirmed evidence of spacetime discreteness, but absence of evidence is not evidence of smoothness. Reference: Emilino Camiglia et al., Quantum Gravity Phenomenology. Rovelli and Vidotto, Covariant Loop Quantum Gravity.
What pixelated really means and does not mean. This is where misunderstandings often arise. Pixelated space does not mean a rigid grid, a digital simulation, square blocks. It means limits, quantization, finite resolution.
just as energy comes in quanta without destroying waves. A final calm thought. Space may be smooth, or it may be grainy, but what physics has already taught us is this. What feels continuous to us often emerges from something discrete, and sometimes, smoothness is just the silence of scales too small to hear. At everyday scales, distance feels obvious. You move closer, you move farther away. Space separates things. But in several modern theories of quantum gravity, distance is not fundamental. It is derived. This is one of the most unsettling ideas in contemporary physics. Distance as an emergent quantity. In classical physics, distance exists first. Objects sit inside it. In quantum gravity, relationships exist first. Distance is inferred from them. In some models, 2 points can be far apart geometrically, but strongly connected quantum mechanically. This means that nearness is not always spatial, it is relational. Quantum entanglement as geometry. This idea gained strength when physicists noticed something remarkable. When quantum systems are entangled, the mathematics describing their connections begins to resemble spacetime geometry. Physicists Mark van Ramsdonk and others proposed, increasing quantum entanglement actually glues space together. When entanglement decreases, space can tear. In this view, geometry is not primary, entanglement is. Space is the shadow of quantum information. Reference: Van Ramsdonk, 1910, Building Up Spacetime with Quantum Entanglement. Brian Swingle, 2012, Entanglement Renormalization and Holography. If distance is not fundamental, then pixelation may not mean blocks, it may mean links. Another serious attempt to describe spacetime discreteness is called causal set theory. This approach is radical in its simplicity. The core idea: instead of space and time forming a smooth fabric, reality is made of discrete events. These events are partially ordered by causality. Before and after come first. Distance comes later. In this picture, spacetime is a growing collection of events linked only by cause and effect. There is no background grid, no coordinates, only relationships. Causality is more fundamental than distance. You can define what influences what can affect what, but without causality, distance has no meaning. Causal set theory proposes that the universe grows one event at a time. Space-time volume corresponds to the number of events. This automatically introduces discreteness. Reference: Raphael Sorkin, Foundational Papers on Causal Sets. Faye Dowker, Causal Set Dynamics. If space is built from events, then smoothness is something that only appears in crowds. In ordinary geometry, you can measure x, y, and z precisely. Order does not matter. But quantum mechanics teaches us that some measurements do not commute. Order matters. Physicists asked a bold question. What if space-time coordinates themselves do not commute? In such a universe, you cannot simultaneously define exact positions. Space becomes fuzzy at small scales. This fuzziness is not due to measurement limits, it is built into reality. Distances blur. Points lose meaning. Why physicists take this seriously? Non-commutative geometry appears naturally in certain limits of string theory, quantum field theory with gravity. Mathematician Elaine Cones developed a rigorous framework for this idea. Here, space is replaced by algebra. Geometry becomes secondary. Reference: Elaine Cones, Non-Commutative Geometry. Doplicher, Fredenhagen, Roberts, 1995, The Quantum Structure of Spacetime. Space may not be made of points at all. Minimal length does not require discrete space. This may sound contradictory, but it is not. How a minimum length can emerge smoothly. In several approaches, attempts to probe smaller distances require higher energy. High energy curves spacetime. This curvature prevents further localization. The result, space resists being divided beyond a limit, but not because it is pixelated, rather because physics intervenes. The generalized uncertainty principle. Some quantum gravity models modify Heisenberg's uncertainty principle. They introduce a smallest measurable length without discrete geometry. This is a powerful alternative. Space may be continuous, yet fundamentally unresolvable. Reference: Garai, 1995, Quantum Gravity and Minimum Length. Kempf, Mangano, Mann, Generalized Uncertainty Relations. So we arrive at a subtle realization. Pixelation is not the only way to limit space. At the deepest level, physics may force us to abandon an old habit. The habit of asking, what is space made of? Instead, the more accurate question may be, under what conditions does the concept of space apply? At very small scales, there may be no geometry, no distance, no where. Only rules, only relations, only transitions. A parallel from thermodynamics. Temperature does not exist for a single molecule. It emerges from many. Likewise, space may not exist for single quantum events. It emerges only statistically. Smoothness may be a collective phenomenon. Reference: Ted Jacobson, 1995, Thermodynamics of Spacetime. Eric Verlandi, Emergent Gravity Ideas.
Black holes are not just astronomical objects, they are laboratories for space-time itself. Inside a black hole, every assumption about space begins to fail. According to general relativity, space-time curvature grows without bound. At the center lies a singularity. Distances collapse to zero. But singularities are not physical objects. They are signs that smooth space-time has stopped working. This is not speculation, it is a mathematical certainty. Einstein's equations simply cannot describe what happens there. Why this matters for pixelation. If smooth space were truly smooth at all scales, singularities would be real points. Physics would allow infinite density, but infinities are not physical. Most physicists interpret them as a signal that space-time must change its nature. Quantum gravity is expected to replace singularities, introduce new structure, possibly discretize space-time. Loop quantum gravity and black hole interiors. In loop quantum gravity, something remarkable happens. When space-time is quantized, singularities disappear. Collapse halts. Geometry undergoes a bounce. Instead of infinite curvature, space transitions into a new phase. This strongly suggests that continuous geometry is not fundamental. Reference: Ashtaker and Bojewald, Quantum Geometry and the Schwarzschild Singularity. Carlo Rovelli, Black Hole Quantum Structure Papers. If smooth space cannot survive inside black holes, perhaps it was never fundamental to begin with. So far, we have spoken mostly about space, but physics does not separate space and time so easily. They are woven together. And yet, time may behave differently. Time in quantum mechanics. In quantum theory, position is an operator, momentum is an operator, but time is not. Time is a parameter. This asymmetry has troubled physicists for decades. It suggests that time may not be on the same footing as space. Some approaches to quantum gravity suggest time advances in minimal steps. Evolution is fundamentally granular. Continuity is an approximation. In causal set theory, new events are added one by one. Time is inherently discrete. In this picture, the universe grows moment by moment. Why discrete time is dangerous. Discrete time introduces challenges: energy conservation, Lorentzian invariance, causality consistency. This is why physicists proceed cautiously, but the idea refuses to disappear. Reference: Raphael Sorkin, Causal Time Growth. Lee Smolin, Time Reality Discussions.
If time itself ticks in steps, then smooth flow may be a macroscopic illusion. Another advanced approach does not start by discretizing space. Instead, it asks, what happens to space-time at extremely high energies? Asymptotic safety. Proposed by Steven Weinberg, this idea suggests gravity becomes scale invariant at high energy. Space-time behaves differently. Geometry softens rather than diverging. Here, space is not pixelated, but its effective dimensionality changes. Dimensional reduction. Surprisingly, many quantum gravity models find the same result. At very small scales, space-time behaves as if it has fewer dimensions, from 4 to 2. This is not philosophical. It appears in loop quantum gravity, causal dynamical triangulations, asymptotic safety. Smooth 3D space fades out. Reference: Weinberg, 1979, Asymptotic Safety. Ambjorn, Jurkowitz, Lowell, Causal Dynamical Triangulations. Space may not break into pixels. It may thin out. Classical geometry is built on points, infinitely small, perfectly defined. Quantum gravity increasingly rejects this. Why points cause trouble? Points allow infinite curvature, infinite energy densities. Remove points and infinities vanish. Several approaches do exactly this. Instead of points, they use extended structures, relations, algebraic entities. Space becomes something you cannot pinpoint. In non-commutative geometry, coordinates are replaced by operators. Localization is impossible. Space is fundamentally smeared. In holography, bulk points are secondary. Boundary data is primary. This is a quiet revolution. Reference: Elaine Cohn's Geometry Without Points. Doppler, Fredenhagen, Roberts framework. If there are no points, then what does pixelation even mean? Some physicists propose a different language. Not geometry, not pixels, but computation. This does not mean the universe is a simulation. Reality is digital, like a computer. It means physical evolution may follow informational rules. State changes may be finite. Transitions may be countable. In some models, space emerges from networks. Networks evolve by rules. Geometry follows afterward. Where this appears seriously, spin networks, loop quantum gravity, tensor networks, ADS/CFT, quantum cellular automata. These are not metaphors, they are mathematical frameworks. Reference: Seth Lloyd, Programming the Universe. Swingle, Tensor Networks and Geometry. We are still inside science, but we are near its edges. At the deepest level, physics may tell us something unexpected. Not that space is smooth, not that space is pixelated, but that space is not a thing at all. It may be a bookkeeping device, a large-scale approximation, a statistical description, useful, powerful, but not fundamental. And yet, every experiment we perform, every observation we make, every measurement we trust, still unfolds in space. So whatever lies beneath it must give rise to it with extraordinary precision. There is a quiet mystery that rarely gets attention. If space-time is not fundamental, if it dissolves into discreteness, relations, or information at tiny scales, why does smooth space-time work so perfectly? General relativity has passed every experimental test so far. Gravitational waves, black hole mergers, time dilation, GPS corrections, all assume space-time is smooth, and they work. This is not trivial. The miracle of robustness. In physics, many emergent phenomena are fragile, but space-time geometry is astonishingly stable. This suggests something profound. Whatever space-time emerges from, it must reproduce smooth geometry with extreme accuracy. This puts severe constraints on any quantum gravity theory. You cannot merely propose discreteness, you must explain why discreteness disappears so completely. Physicists borrow an idea from another field. In condensed matter physics, many different microscopic systems produce the same macroscopic behavior. This is called universality. The idea is that smooth spacetime may be a universal large-scale phase. Details at the smallest scale may not matter. What matters are symmetries. Reference: Nigel Goldenfeld, Universality Concepts. Butterfield and Isham, Emergence in Physics. Smooth space may be inevitable, even if it is not fundamental. One reason spacetime looks smooth is symmetry. Symmetry is not decoration, it is enforcement. Lorentz symmetry. Special relativity tells us the laws of physics are the same for all observers. No preferred frame, no preferred direction. This symmetry severely restricts spacetime structure. If space were crudely pixelated, Lorentz symmetry would break. Directional effects would appear. Experiments show Lorentz symmetry holds to extraordinary precision. This suggests either space is truly smooth or discreteness is hidden extremely well. How discreteness can hide? Some theories preserve symmetry statistically, like random lattices, dynamical triangulations, no fixed grid, no preferred direction. Symmetry emerges on average. Reference: Mattingly, Tests of Lorentz Invariance. Amjorn et al., Causal Dynamical Triangulations. Symmetry may be the mask that hides spacetime's true nature.
We take the dimensionality of space for granted. 3 dimensions. Always. But quantum gravity suggests otherwise. Dimensional flow. At large scales, space behaves as 3-dimensional. At very small scales, many theories predict effective dimensionality decreases. This phenomenon is called dimensional flow. Measurements of diffusion processes in quantum spacetime models show near the Planck scale, spacetime behaves like it has 2 dimensions. This is not philosophy. It appears in causal dynamical triangulations, asymptotic safety, and loop quantum gravity. Why fewer dimensions help? Lower dimensional spaces are better behaved mathematically, avoid infinities, tame gravity. Nature may simplify itself at small scales. Smoothness fades not into pixels, but into less space. Reference: Carlip, Dimensional Reduction in Quantum Gravity. Amjorn, Jerkovitz, Lowell, CDT Results. Space may not shatter, it may thin. When physicists speak of a smallest length, they do not mean a ruler with marks, a smallest brick. They mean something more careful: operational meaning. A smallest length means no experiment can distinguish distances smaller than this scale. This could arise because measuring devices disturb spacetime. Energy curves geometry. Localization collapses. The universe resists precision. Length without geometry. In some theories, length is not a property of space. It is a property of interactions. Distance is inferred, not given. Reference: Garai, Operational Limits in Quantum Gravity. Mead, 1964, Minimal Length Arguments. If length is operational, then pixelation is a human metaphor. At very small scales, spacetime may not be definite. It may fluctuate. Quantum geometry fluctuations. In quantum gravity, geometry has uncertainty. Distances fluctuate. Volumes are probabilistic. Space is no longer a background. It is a quantum system. Consequences. This leads to fuzzy causal structure, blurred horizons, indeterminate geometry. Yet somehow, the universe averages itself into calmness. Reference: Wheeler, Quantum Foam, Ravelli and Vidotto, Fluctuating Geometry. Order may be statistical. At this depth, physics does not speak loudly, it whispers. Some theories say space is discrete. Others say space is continuous but unmeasurable. Others say space is emergent and secondary. All agree on one thing: the question itself is pointing us in the right direction.
One of the most surprising ideas in recent decades is this: gravity may not be fundamental. This statement is not philosophical rebellion. It comes from precise mathematical work. Gravity as an emergent phenomenon. In 1995, physicist Ted Jacobson made a startling discovery. He showed that Einstein's field equations can be derived from thermodynamics principles alone. Not assumed, derived. Specifically, the laws of space-time geometry follow from entropy and energy flow. This means gravity behaves like pressure or temperature, and pressure is not fundamental. If gravity emerges from thermodynamics, then space-time curvature is not primary. Geometry is a macroscopic description. Microscopic degrees of freedom must exist. Smooth space-time may be like temperature in a gas, continuous but not fundamental. This strongly favors non-smooth microstructure. Reference: Ted Jacobson, 1995, Thermodynamics of Spacetime. Padmanabhan, Gravity and Thermodynamics. If gravity is emergent, then the stage it acts on may be emergent too. We return to black holes because they refuse to let this question go. The area law problem. Every ordinary system stores information in its volume, but black holes do not. Their entropy scales with surface area. This is deeply unnatural for smooth 3D space. It suggests degrees of freedom scale differently. Volume is secondary, area is fundamental. This is one of the strongest hints that spacetime is not continuous in the usual way. If information is stored on surfaces, the interior geometry may be emergent. Smooth space may be a reconstruction. Reality might be counted, not filled. Reference: Bekenstein, 1973, Black hole entropy. Hawking, 1975, Black hole radiation. Susskind, holography. Space may not hold information. It may display it. We spoke earlier about entanglement gluing space together. Now we go further. Entanglement entropy as distance. In holographic models, distance between regions is proportional to entanglement strength. More entanglement, regions appear closer. Less entanglement, space stretches. If entanglement vanishes, space disconnects. Geometry dissolves. Wormholes and entanglement. A famous conjecture in modern physics is ER equals EPR, proposed by Maldacena and Susskind. It suggests entangled particles are connected by tiny, non-traversable wormholes, not as tunnels for travel, but as geometric expressions of correlation. This is not fantasy. It emerges naturally in equations. Reference: Maldacena and Susskind, 1913, Cool Horizons for Entangled Black Holes. Van Ramstaan, Entanglement and Geometry. If entanglement weakens, space itself may loosen. Given all this, one might expect spacetime to easily fragment. It does not. Once spacetime emerges, it is extraordinarily stable. Fluctuations average out. Geometry becomes rigid. This is similar to elastic solids, hydrodynamic flows. Many microstates, one smooth outcome. The analogy with sound. Sound waves are smooth, but air is made of molecules. You do not hear the molecules. Likewise, we do not experience spacetime's microstructure. We experience its collective behavior. Reference: Lauthlin, Emergence and Rigidity. Padmanabhan, Spacetime Elasticity. Smoothness may be unavoidable. Now we move to the beginning, or rather, to the moment when beginning may not apply. Before spacetime geometry, near the Big Bang, energy densities were enormous. Quantum effects dominated. Classical spacetime equations fail. Many models suggest spacetime did not yet exist. There was no before, only transitions. Quantum cosmology. In approaches like loop quantum cosmology, Hartle-Hawking no-boundary proposal, the universe begins without a singular point, without classical time, without smooth geometry. Space condenses out. Reference: Ashtekar, Loop Quantum Cosmology. Hartle and Hawking, no-boundary proposal. Space may have formed the way crystals form out of cooling chaos. At this depth, physics becomes careful with language. Real does not mean fundamental, indivisible. Real means predictively stable. Smooth spacetime is real because it works. Pixelation is real if it explains deeper behavior. Both can be true.
If space can emerge, a quiet question follows. Can space disappear? Physics does not answer lightly, but it does not dismiss the idea either. Phase transitions of space-time. In ordinary matter, ice melts, water boils, order appears and disappears. Some physicists believe space-time itself may undergo phase transitions. At extremely high energies, geometry dissolves, distance loses meaning, smoothness vanishes. At lower energies, space condenses, geometry stabilizes, continuity emerges. This suggests smooth spacetime may be a phase, not a necessity. Reference: Oriti, Spacetime Phase Transitions, Amjorn et al., Quantum Spacetime Phases. Space may not be eternal, but neither is smoothness fragile. If space is discrete, or relational, or informational, why does everyday life feel so continuous? Just as a beach looks smooth from afar, but granular up close, space-time's microstructure averages out, cancels irregularities, preserves geometry. Your body, your senses, your instruments are simply too large. The silence of small scales. Quantum geometry fluctuations occur far below atomic scales, leave no imprint on daily experience. Smoothness is not deception, it is stability. Reality does not hide from us, it simply speaks softly where we cannot hear. After decades of work, physics says this, plainly. We do not yet know whether space is smooth or pixelated, and anyone who claims certainty is stepping outside science. What we do know is this: smooth spacetime works extraordinarily well. Quantum gravity strongly suggests limits. Multiple independent approaches point to new structure, but they disagree on details. This is not failure, this is healthy science. Refer to Rovali's cautionary statements on quantum geometry and Smolin's limits of current theories. Uncertainty is not weakness, it is honesty. It may be that space is smooth when many degrees of freedom act together. Space is granular when examined too closely. Space is relational at the deepest level. Space is emergent rather than fundamental. These ideas do not contradict, they layer. Like water, molecules, quantum fields, sound, air, atoms. Smoothness and pixelation may both be true at different depths. Reality often refuses single answers. This question is not about curiosity alone. If spacetime has structure, black holes behave differently. The universe's beginning changes. Quantum gravity becomes testable. Understanding space means understanding the limits of measurement, knowledge, and prediction. It tells us what questions make sense, where physics must stop or evolve. To ask what space is made of is to ask what explanation itself is made of. Tonight, as you rest, the space around you feels smooth, reliable, unbroken. And for all practical purposes, it is. But far beyond sensation, far below atoms, far beneath measurement, physics whispers another possibility. That space is not a thing, but a pattern. Not a container, but a relationship. Not infinitely divisible, but quietly finite. And yet, it gives rise to stars, to time, to thought, to rest.
Whatever its true nature is, smooth or pixelated, it holds you just the same. If you enjoy exploring questions at the edge of physics and meaning, you may quietly subscribe to The Wandering Neuron. New journeys continue slowly.